Welcome, Regents students. The topic of today's video is nuclear physics. We already started nuclear physics in the last video, but as I mentioned, I felt that the topic was too long for one video, so I split the topic into two videos. Let's just jump right into the idea for today, that mass energy is conserved, the conservation of mass energy. You learned in chemistry class, maybe in other science classes, that mass was always conserved. That is not true. The initial mass of a system does not have to equal the final mass, and same with the initial energy and the final energy. What's conserved is mass energy together by the equation E equals mc squared, Albert Einstein's famous equation. What does that mean? So, it's possible for there to be more mass before than after. In other words, mass seems to be lost by a system, or is lost. And I'm not talking about in chemistry class, when you did an experiment and you found that the products had a less mass and you said, oh, well, maybe we had evaporation and some atoms disappeared in the atmosphere or escaped in the atmosphere. No, even if you capture every single atom, every single electron, every particle, and you contain it within a system, it's possible for the system to still lose mass if the system is exothermic. If it's releasing energy into the environment, then its mass is decreasing. It's possible to go the other way. Maybe the final mass is greater than the initial, so we gained mass. Again, no matter's going in, no atoms. You're keeping all the same number of atoms, but somehow you have more mass. That's possible if the system is endothermic. In other words, it's absorbing energy from the surroundings. If you lose energy, you lose mass. If you gain energy, you gain mass. Mass energy is conserved. Okay? Let's suppose in a particular experiment you have 1 gram lost. So you capture all the atoms that you had before and you measure them, and there's 1 gram missing. Totally fine. It's okay. It's possible. So how much energy was then released to the environment? You use E equals mc squared, which, by the way, is in the reference table, so you don't need to memorize that. See, here's the modern physics section, and we have E equals mc squared. C, of course, is the speed of light. You don't have to memorize that either. So we go to the front cover of the reference table, and right here near the top, we've got the speed of light in a vacuum, 3 times 10 to the 8th meters second. Just a reminder, this is actually the speed of all electromagnetic waves, including gamma rays, microwaves, so on and so forth. Just a reminder, it's 3 times 10 to the 8th. That's C. That goes in there. The 1 gram has to be converted to kilograms, so we do that as 0.01 kilograms, and then we plug in 3 times 10 to the 8th, we square that, and we get 9 times 10 to the 13th joules. An enormous amount of energy. That is about the amount of energy that's released in the first atomic bombs that we invented, the ones we dropped on Japan. So if you could gather, after those bombs blasted, every single atom in the casing and everything, every single neutron that shot out into space, and you gather them, somehow magically pull them back, you would find out of the whole bomb there was a gram that was no longer there, because that energy is now all in the world. It melted glass, it boiled water, that energy disappeared or went into the world, so did the mass with it. Okay? Now, before I move on to the second method, I just want to point out that, as I said, this has been true even in all your chemistry experiments, even in everyday life. You just never realized it was true. Let's suppose I take a glass of water like this, okay? So, of course, there's no water in there because then I'm tilting it to the side so you could see it. You can see it's a big glass, right? I fill it with water, ice water, 0 degrees Celsius, and I put it in a microwave and I boil it. So I'd fill about half a liter in here, which would be, roughly speaking, about 1 pound of water. So you feel like you know what a 1 pound weight is like. That's going into the microwave. I take it from freezing to boiling, okay? So how much energy is that? Well, you could look up the chemistry equations and calculate, and you'd get around 200,000 joules, a lot of energy to boil that much water. So as I'm putting the energy in with the microwave, we are also putting in a certain amount of mass, right? And you didn't think, well, did I really put mass into the water? Okay. How much mass went into the water? How much was added by the microwave? I use E equals mc squared. The energy I put in the water is 200,000. That means I put in a certain amount of mass. I plug in speed of light and I get, when I solve this by dividing by 3 times 10 to the 8th squared, I get 2.2 times 10 to the minus 12th kilograms, which is this many grams, which in a decimal form is like this. So you take this out of the microwave and suddenly it's heavier. It's heavier by this much. And this is why you never realized that E equals mc squared was true your whole life. Because even when you put an enormous amount of water into the microwave and boil it, it's not like you come and pick it up and say, oh, it's so much heavier now, right? You don't feel that difference because it's not even a feather's worth of mass that was added to that water. But it's true. Albert Einstein discovered the water really is more massive and therefore heavier. And just to give you an idea of how small that is, in college I used an electronic balance that went down to this. It was so sensitive that the pan that I put the samples in my chemistry class had to be enclosed in a glass case because just someone walking by would create enough of a breeze to start changing this measurement right here. So you need it in a perfectly still environment. So that's how little this is. And boil water and you're adding that much mass. Okay, minuscule amount of mass corresponds to an enormous amount of energy. So you don't normally notice the mass change. Always happens though, always. Okay, the other method is when you're dealing with single atoms. Remember how I said to measure this pencil in miles would be obnoxious? I'd say like 10 to the minus 6 miles. So we use inches or something like that. Well, same thing when you're dealing with single atoms. The kilogram mass is way too big. So there's another symbol that we use. The atomic mass unit in the Regents, they just use a symbol U, but often on the internet you'll see AMU. But we're going to use the symbol U. That's what's in the reference table. And it corresponds to roughly the mass of a proton or a neutron, slightly less. Proton 1.67 10 to the minus 27th, and neutron also. So it's a very small amount of mass. And sometimes the problems in the Regents, they tell you how much atomic mass units are gained or lost. Okay? If you wanted to find the energy that corresponds to that gain or loss, you could use this conversion to convert this to kilograms and then plug it in here and get an answer. But that's not how it's done on the Regents. What you do is you just use a conversion. You can convert the mass to energy, right? This is mass right here, using a dimensional analysis approach. Now, what I do is I put a fraction, I put atomic mass units on the bottom, so that they'll cancel and leave me energy in the top. But what's the conversion between mega electron volts and atomic mass units? Front cover of the reference table. So here's the first table here. Near the bottom here, we got one universal mass unit, and we see 9.31 times 10 to the 2, or 931 mega electron volts. So I knew I was going to put atomic mass units in the bottom and mega electron volts in the top. The numbers I get from the reference table, 1 goes with the U and 931 goes with the mega electron volts. Now what happens is the U cancels and I'm left with multiplying this times that and dividing by 1, or 18.6 mega electron volts. A reminder, mega means 10 to the 6th, right here. Mega 10 to the 6th. So it's 18 million electron volts. 18.6 million electron volts would be the result of that energy. And since the mass is gained, that means the energy went into the system making more mass. That's what this is all about. Let's take a look at another example. Okay, this is a little bit more involved. So the question is asking, determine the energy of the following reaction and state whether it is lost or gained. This is what we call a fusion reaction. Okay, so we got two hydrogens coming together to form a helium and a neutron left over. So what you need to solve this, you need to know the masses of each particular hydrogen So that has to be given to you. You don't have to memorize that, and it's not on the reference table. So I get these, and then the mass of the helium and the mass of the neutron. What I do is I find the mass initial, or the mass of the reactants. Take these two, add them together, I get that. Then I find the final mass of the system by adding those two together, and I get that. Now notice, mass is not conserved. I gained mass. How do you gain mass? When energy goes in, mass goes in. Okay, so that's what I know. Mass was gained, so energy was absorbed. Okay, how much energy? Well, what I could do is I could find the change in energy by subtracting these two, right? Final minus initial, that's what I got here, and then I got the answer. And then I do that dimensional analysis conversion as I did over here. I start with the units, and then I multiply by a fraction, and I put the atomic mass units in the bottom, so it'll cancel and leave me mega electron volts. I go to the front cover of the reference table, I see that 1 goes with the unit and 931 goes with mega electron volts. So I'm taking this, multiplying, and then dividing by 1, and I get 9.01 mega EVs, mega electron volts are absorbed. So just find the change in the mass of the system, and then do your conversion as we did over here. One more example I'm not going to go into too much detail on. Okay. So determine the energy change for the following reaction. We've got one hydrogen and another one combining to, so this is like another fusion reaction of two hydrogen atoms. Okay, and then, oops, wait a minute, I meant to write helium here. So I've got the masses of the reactants, and I just plug them in right here, and I get a total of 3.022. And then, of course, the final is just the final mass of the helium. This, as you can see, mass decreased in this case. We lost mass to the world, so that means energy went. That's how you lose or gain mass. When energy goes out into the world, so does mass. When energy comes in from the world, so does mass. Okay, so then I don't do the rest of this because the rest is details, but basically I just find delta M, subtracting those, and then I do that conversion again. Not important, because we already saw that example. Final example, I just want to point out that sometimes you can convert from energy to the mass in atomic units by doing the opposite conversion that we saw on the previous page. So here we start with the energy 9.01 mega electron volts. What if we wanted to find the mass? Well, what we're going to do is put mega electron volts on the bottom so that the mega electron volts cancel, leaving us the atomic mass units. And then once again, we go to the front cover of the reference table to find that conversion, right? So right here, 1 unit to 931 mega electron volts. So now what we're doing is we're taking this and dividing by 931, and we get the mass back. So whether you have units on the top, mega electron volts on the bottom, or the other way around, depends on which way you're going in your conversions. Okay, so that's today. Mass energy is conserved. Systems don't have the same mass throughout, neither the same energy. If energy is absorbed, so is mass. When energy is released, so is mass into the world. And then you could do E equals mc squared or a conversion. Okay, so that's the second part of nuclear reactions. Okay, so I'll see you in the next video, which is on pair production and pair annihilation.